Hi, and welcome to EP2CM4. This is going to be an overview of the design project. So what you're going to do for the design project is to pick a hypothetical engineering design decision, which you'd like to make that requires mathematical modeling, and model it using Python to script a FlexPDE simulation of it, and then find the optimum value of a parameter for your particular design. So examples of this would be, imagine you want to build a thermal strap, let's say, to cool down a computer on a satellite, and you only have conduction to do it. Then you want to design the optimum, let's say, width of this thermal strap so that it weighs as little as possible, but keeps the temperature below a certain limiting temperature, let's say 60 degrees C, after 12 minutes of operation. Right, so that would be the sort of thing that you could optimize using simulation in FlexPDE and then script it using Python. What you actually hand in is an explanation of the background of the particular application that you're designing for, including explaining the constraints and the things to optimize. So for that example, you would explain, all right, imagine we have some satellite and the chip on it, the computer chip is generating, is like this dimension is, let's say, 1 centimeter by 2 centimeters by 3 centimeters of a rectangular prism. So this is like that's the shape of it. Ideally draw it out. That would be a spot to include a figure, and say what heat it generates, and that there's no heat dissipated to the sides. And what we need to do is design a thermal strap that's going to get the heat away from this thing into a reservoir that's, let's say, at some fixed temperature of 20 degrees C. And what we need to optimize is the thickness of this thermal strap given a fixed width, or maybe the width given a fixed thickness. If the material is determined, optimum being minimum weight that would get the certain temperature, that would make sure that the temperature of this computer chip stays below a certain amount after a certain time. So you specify all of these things in there, explaining it out. That's the point of the first thing, so that at the end of it, we know exactly what we're going to be optimizing, what the parameter is, everything like that. Now, part two, physics of what you're going to use to solve the problem. In that situation, there's not a whole lot to write up. It's the heat equation, and we've got a lot of the write-up already in the notes that we did in the course. You're pretty familiar with it. So this section might be a fair bit more if you have a non-standard kind of physics thing that you're simulating, non-standard partial differential equation. Imagine you're not just doing the heat equation, but you want to be ambitious with this project and build in something different, like Navier-Stokes equations to do fluid flow or something like that. Then this would be a fair bit longer. In the heat equation situation, you still would explain the justification for the boundary conditions that you're planning to use, what the physics means of all of this. You'd go into documenting and explaining what the heat equation does. So just because we did it in the course doesn't mean that you don't want to explain here what you're using. Imagine it's a standalone thing that people would be reading if they haven't actually taken EP2CM4. Next part, you go into more detail of how exactly you incorporated it into FlexPDE and testing a known case. So this means you simplify the problem, or you do some specific example of it. So if you can do an analytical solution for one version of your problem, then do that. You can also check out edge cases and see how things scale and what you would expect. So make sure that let's say in the thermal strap example, if the width gets very large, then the temperature of the computer chip gets basically to the temperature of the reservoir. It stays at 20 degrees the whole time. Whereas if the width is very small, then the temperature gets too high. It gets above the amount that we wanted pretty quickly. So this is the kind of thing that you'd want to check with this. You can check edge cases. If you don't have analytical results for an exact known case, then you can at least check edge cases. You can try and simplify the problem so that you can check an analytical result, even if if it doesn't tell you the optimization, that's totally fine. That's the point of this one. Just make sure that your simulation is working in as many ways as you can by doing edge cases, by checking the scaling of results, meaning as you change one parameter, how does the optimization change? How do things inside of it change, like the temperature, the heat flux, those sorts of things. Talk all the way through this and look at those results. That's the point of this part. Next thing you do is talk about how you incorporate this into Python and script running the model. So this is scripting the FlexPDE thing that you set up in part 2 to zero in on the optimization of this parameter that you're looking for to give you the best engineering design for your particular application. That's the point of this section here. Show how you incorporated it into Python, and then run through the results on the way of zeroing in on the optimum design choice. But save the detailed discussion of the results and their meaning for for the conclusion here, the results discussion thing here at the end. So this is where you can also talk about the meaning, maybe some follow-up, how well you believe this thing. This is the idea in part 5. Part 4 is actually similar to what we did in some of the assignment bonus questions. So zeroing in on this optimization, dealing with noise perhaps and curve fitting, doing gradient descent and grid searches. Those are the sorts of things that you'd want to get into in part 4. Part 5, more about discussing the meaning after the results of the simulation are already achieved from part 4. Then include a bibliography for everything that you need to reference, and the code for both Python from part 4 and the FlexPDE stuff from part 3 as separate files digitally. So you submit this, you don't actually print off and hand in the design project, you submit it on the Dropbox and Avenue, and so you can just include these things as separate files. You don't have to include them in like printed off format or something like that. Okay, now even though you're doing that, you can still take sections of them as you're bringing them in, and you should do this to discuss it. Like when you're talking about bringing in or making the FlexPDE simulation, if it makes sense to talk about certain parts of it directly in the text, then you can bring that in here and refer to like an appendix where the code is, if you like. And same thing here, as you're talking about building in the script in order to zero in and find your optimum of the for your particular design decision, then you can talk about segments of the Python code if they're interesting and are useful for explaining your point here in section 4. Marks for this are based on how clearly and concisely you present a report that satisfies these criteria, how extensively you've applied computational multiphysics to solve a substantially challenging problem, the accuracy, believability, and insightfulness of your analysis, and the overall joy to read as an engineering report. A little bit on the different sections. So the first section, modeling problem and goals description, is out of 5, background physics out of 8, programming and testing the model 10, optimization 10, discussion and final meaning 5, and then some marks on presentation and formatting, which includes stuff like the references, that sort of thing, and then overall impression, which is a big blanket thing that isn't married to one section in particular. Let's go over some tips. When you're writing, it's most important to be super clear, right? So you see that some of the marks here are based on how clearly and concisely you present a report that satisfies the criteria. It's more important to be clear than it is to be formal, so passive voice isn't required. What I'm talking about here is rather than saying something like a thermal strap will be used to cool an onboard computer system. Rather than saying something like this is okay, very kind of passive. See this idea here, will be used. It doesn't say who's going to do it, right? Passive voice is something that you might want to do in order to diffuse responsibility, right? So to say, if you're kind of embarrassed about who did a thing, or if it's in the past tense, you could say a thermal strap was used, or a thermal strap has been used. It makes it unclear who actually did the thing, which maybe you would say if you're if it's like the king has done this, right? But you don't want to throw the king under the bus. So you say, oh, well, the thermal strap has been used to cool an onboard computer system. That might be a way that you would speak there in passive voice. But it's deliberately designed to kind of hide information, right? And that's not what we're all about in engineering. So it's much better for this report for you to be more clear, right? Formality is not as important as clarity. So say something, if formality means you're going to write like this, where it makes it unclear what you're actually doing, then say, in this design project, I want to design a thermal strap to cool an onboard computer system. Right, so this is kind of the same sentence, still isn't maybe ideal, but this is the same sentence in an active voice. Right, so you're saying, you want to do this. Okay, now the reader knows exactly what you're talking about. You're not saying, oh, this is going to be used maybe by NASA in the future or something, but this is talking about what you're going to do in this project. Even though this is a lot less formal, the clarity that's added from this is more important. So if writing in passive voice means you're going to be unclear about things, then sacrifice the passive voice if necessary. Next thing, let's talk about formatting, unit formatting. The NIST formatting guide is a fantastic reference to explain how you should format a lot of things. So an example of this, of some rules in here, are the typeface. So variables and quantity symbols are in italic typeface, meaning that when you have T for time, you put this in italic, whereas unit symbols are in Roman type. Like this, seconds. Notice that it's not italic, right? So T is the time and S is seconds. So temperature is 22 Kelvin. Notice the non-italic there. Another thing to notice is that the number is in Roman. There's a space between the value and the units. So all of these things, there's a bunch of them in this formatting guide. I suggest you read it through and incorporate this into your typing. Now, in typing equations, I use MathType, but that all depends on whether or not you should use this or just the built-in equation editor is totally up to you. There's lots of things that you can do with MathType or the equation editor. So you can say, like, let's say sigma is equal to 7, and then if it's in MathType, it's Control-Shift-Space to insert a space, which you're going to need to do between numbers, values, and units. So for what could sigma be in? Sigma could be like a charge density. So maybe this is going to be 7 coulombs per meter squared. So surface charge density here. Kind of a large surface charge density, but yeah, here we go. So now we've got a thing written out using Roman for these. To do this, I typed Control-Shift-E rather than Control-Shift+ to make it like the math version. This would be not correct. Control-Shift-D to make it in the Roman typeface. Now that's because MathType is like a commercial piece of software. You might consider using just the built-in equations within Word. So let's practice that. Here's a new file that we're going to be using for this. Let's try insert equation. If we first type, here's an inline equation. When might we use an inline equation? We'll say the mass is equation. Now I'll type m space equals 5 kilogram. And we want this to be not italic, so we go Control-I after that. All right. Fantastic. The mass is m equals 5 kilograms, and now we're out of the equation, put the period after that, since it's part of this sentence. All right, now we did that by clicking on Insert Equation. If you wanted to insert an equation, you can hover over this, and it tells you that it's Alt equals in order to do that. So that's in the thing that's just being, that's showing up right under this, insert an equation, Alt equals. Yeah. So let's try that. If we go Alt equals, it does that. Because we had nothing on this line yet, it automatically will center justify it, but we could change it with Control-L to make it not a center justified thing. There's lots of hotkeys within the equations to do this. So you can just try inserting brackets and type things within that. You can try backslash and then sum to get a sum. There's all sorts of different ones. To get a feeling or to understand what these hotkeys are within the equation editor, if you want to learn a bunch of them and get to super speed with it, you can go to Options, and I believe it's in Proofing, Autocorrect Options, Math Autocorrect, and then look at what all of the different hotkeys are within the equation editor for the different things you might want to insert. So we've got like the I int would be like a triple integral. Oh, that's a quadruple integral. 4 i's. Yeah, that makes sense. What else do we have? We've got the OI int, which is a double, so circle double I integral, that is. Yeah, so all kinds of things in here that you can look at and see what they would be. Now a neat thing to enable if you want to get math autocorrect working all the time is this. This is not enabled by default. Use math autocorrect rules outside of math regions. So what's neat about that is once that's turned on, you can just type a backslash OINT and then get this symbol right when you're regularly typing. Now that's kind of a weird symbol to have just in the middle of a script, but where it's useful is with the degree C one. So if you go deg C, it's this, deg C, yeah. So that's kind of convenient because a lot of the time you're typing things, if you wanted to say things that have to do with temperature. Let's say the boundary temperature is fixed at 20 space deg C. Okay, and now we've got the degree symbol in there. It looks all nice. It's a lot better than just using a superscript 0 or superscript small o. This is going to give you a spelling mistake and Word will flag it. Hey, what are you doing here? This is just like an OC. Do you mean orc? No, cow perhaps? So it's much preferred to just use the degree symbol there. The boundary temperature is fixed at 20 degrees C. Another thing that you can do is insert a non-terminating space between your values and your units. Let me show you what I mean by that. So let's imagine we start typing this all the way across a line and we get it so that it's going to be wrapping onto the next line, right? If we narrow this page enough, then it splits it in an inconvenient spot, right? So it split it between the 20 and the degree C. You really don't want that. How can we avoid it? Well, rather than putting this space in here, we can put a non-terminating space. Let me show you what this means with the field codes. If you do Control asterisk, you can turn on these invisible codes for white spaces. You see everywhere there was a space, there's this little dot now. This is showing us that there is a space there with something visible. There's all kinds of different white space involved, right? So there's line breaks here. That's what these, I guess, backwards P-type looking things are. These are line breaks or carriage returns. Then there's a regular space here. But you see this one, this is a big thing. It looks kind of like the degree symbol itself, actually. That's a non-terminating space. How you do that is with Control-Shift space in Word. So Control-Shift space, it looks just like a regular space, but it's non-terminating. You do this anywhere you don't want it splitting a line break. And an example of that is in these areas between values and units. Next thing that I want to talk about is proper use of headings. So with Alt-Shift left arrow, I can get into this first heading. So we might say section 1, which is Introduction. Introduction, background physics, and then we're going to have background physics. Incorporation, optimization, and then we will put in what's next. We've got the scripting. Oh, that's in the optimization section. Then we've got the results discussion. Results, and then we've got references. Okay, and maybe we've got some appendices after that. Now within each of these, we can, so these are headings, right? If we put in, this is where we explain the problem, heat equation explanation, etc. Now, by making these proper headings with the Alt-Shift arrows, promoting it to heading 1 or heading 2 or heading 3 or something like that. If you like, you can just click it instead. What's nice is it auto-populates this navigation toolbar over here. So now we can jump around to different headings within the document. We can click on references and go right to there. We can click on introduction and go right back up to there. Very good and useful in a very big document. Another thing that this lets us do is at the beginning, we might insert an object. No, that's not it. Insert, let's see. Quick parts. Field, yes. Okay, under fields, there's a lot of built-in ones like a table of contents. This is a very useful one. Now, you can customize it by clicking the buttons that were on that page instead. What this does is it automatically populates it with all the headings that we had. Now, suppose you've got subheadings, right? So we're gonna have in here maybe the heat equation, and maybe we're also gonna explain Joule's law. Okay, now what we can do is, even though we added some things afterwards, we changed some stuff, maybe we decide we want to call this FlexPDE incorporation in particular. Now up here, we right click and then go update field, and it will add in any new headings that we added afterwards. To make it even easier to read and navigate through this thing, you might also consider inserting a numbered list here. Let's see. So there's a special kind of list that you can use called this one, multi-layered list, multi-level list. Yeah. Okay. So this one includes automatically all the different headings with an appropriate number in front of it. We could have specified the formatting for this by picking a different one. So you can use this one if you just want it to be like numbers with points after that. And then as you'd expect, it updates it automatically in the heading section and updates it automatically in something like a table of contents if you want to have something like that. Now your headings are not going to look like this by default. Believe it or not, I actually wanted them to look like this. This is something that I made up here. You can change it. You can change the heading to whatever you like. So let's suppose we wanted to make it just look totally different. Right? We could maybe get a new line. Heading sample style. Let's maybe change the font. I know some people these days are kind of anti-Times New Roman, so whatever you're into. Let's take Arial Black here, and we could do like a fancy word art thing. Actually, let's see if we can get something that looks even better. Oh yeah, check that out. Now, insert an underline. Control U. Okay, looks pretty good. Next, what we'll do is highlight some of this or even select somewhere there and then say, right click, update heading 1 to match selection. And what that does is it automatically replaces all of the headings, all of the heading 1 things with something that looks like this new style. We can even eliminate this afterwards and get rid of that extra thing. And there we go. It's all written in. We've gotten rid of our multi-leveled list, but we could add that in again. Okay, so now you can make your headings look like whatever you like. If you save this to your normal file in Word, then you can even preserve this across computers. As an aside, if you want to do this, then the way to do it, at least at time of recording, is to run app data within Windows and then go into Microsoft templates and then put normal.m in there. You can copy the normal template from Word if you're going to be switching computers, and then save it to another to some cloud storage thing and copy it back over when you're done. So that way you can preserve when you get a new computer, that is, copy it back in to this location, and it should work. So for Excel, it seems to be Microsoft Excel start for your personal.xlsb. Same kind of idea. This is preserving settings in Word and Excel from one computer to the next. The last thing I want to talk about today is using a reference manager like Zotero. There's other ones. Zotero is just the one that I'm familiar with, so I'm going to talk you through what that is. You'll get a program that you'll install kind of like this. You make an account on it, and then you can save things into this Zotero library. Let me show you how this works. Imagine we wanted to reference this SI unit formatting convention thing from NIST. Well, once we've got Zotero open, then we can click this little button here, save to Zotero, save it to EP2CM4. Sure, it's saved there. And now in our library here, it keeps track of this reference from one computer to the next. You could log in on this somewhere else. If we ever lost this page, we could double click on this and open it up again. What else the other thing that's really useful for this is now within Word, we can make a reference to this. So we'll say formatted according to the NIST guide. You don't actually need to reference the NIST formatting guide when you're typing a report. This is just as an example. You might reference like material properties. You might reference a FlexPDE sample file, something like that. So let's add and edit the citation, and it gives us a chance to explain what style we want to use. Let's use IEEE style. And now we can start typing in something. So we'll type in, let's say NIST maybe, or unit, SI unit rules and style convention. So it found it from that, hit enter, type that in, and now we've got this right here. Formatted according to the NIST formatting guide. Because we picked IEEE, it's automatically referencing things in IEEE format. If we later include another reference, like let's imagine properties, add and edit citation, 6061, so aluminum 6061 alloy, and then we've got also the gold reference. We can put both of these in at once, I think. So let's add and edit citation, 6061, gold. Okay, so it automatically puts in the comma. It keeps the list all working for us. And now let's suppose we change it later. So at the beginning, we decide, we actually also need to reference the page for gold up here. Look at that, it automatically renumbers everything. So this was reference 2 down here, and now it became reference 1, all in order every time. Perfect. Then when everything's done, you can insert a bibliography at the end, and it automatically adds in everything that you referenced. Now, I never had to type this out at all. I just went to the website that I was using on the NIST formatting guide, and then hit that one button, and it put it into Zotero all automatically. Big time saver. Okay, one bonus tip. While you don't have to use new physics in this design project, you can just use stuff that we dealt with in the course, like the heat equation, steady state, electrical conduction, dielectrics, that sort of thing. If you are going to do new physics and you want to sort of break out and do the more challenging version of incorporating brand new physics into FlexPDE, then a good place to start for inspiration is in the help files for FlexPDE itself. So within here, there's a bunch of sample problems on different applications. And what's nice about looking at these is it starts you off with stuff that Flex has some hope of being able to model. So if you wanted to say, is it possible to do chemical reactions in FlexPDE? Well, you can examine something like this reaction PDE example and see what they're able to figure out here, right? See how this thing works and try and try and build the design around modifying this problem in order to solve what you're interested in solving in particular. Can you do lasers in FlexPDE? Can you do some certain groundwater simulations within FlexPDE? Yeah, so these are the sorts of things that you might want to start off with if you're determined to use finite element methods. Check out the sample problems to see the sort of things that FlexPDE handles particularly well.